Dijkstra'S algorithm.
Suppose you have a graph connected by weighted edges like this one. Then Dijkstra'S algorithm allows you to calculate the shortest path from one node to every other node. This can be applied, for example, in digital mapping. So suppose those are cities and the roots are the edges. Then Dijkstra'S algorithm will allow you to calculate the distance from one city to every other city. Let's take a look at this graph. And suppose we want to calculate the shortest distance from A to every other node in this graph. This can be easily done in Dijkstra's. The first information we need to keep track of is which nodes we have not visited yet. The first step is to mark all nodes as unvisited. So therefore we create a list of unvisited nodes that contains every node in the graph, and also visited nodes that is empty in the beginning. And the second step is we assign to all nodes a tentative distance value that will be changed over time. So therefore we can use this table on the right, which consists 3 columns, the node, the shortest distance from A to this node. So in the beginning of this algorithm, we know nothing any distances to any other node. Then we set A to 0 because the distance from A to A is 0 and every other distance we set to infinity. And in the last column is the previous node that leads us to the shortest distance. And this column will be empty in beginning because currently we have no information about this. Now we can start the first iteration. Since we start at node A, we start by calculating the distance to all unvisited neighbors from A. The distance from A to B is 4. And the distance from A to C is 2. And now we can activate our table on the right. If we found a new shorter distance to one of the unvisited nodes, so the B and C are unvisited, and the current distance is infinity, and now we can update A to B to 4, and store A as the previous node in the table. The same applies to the node C. We can update the shortest distance to C to the value of 2. And now the iteration ends here and we can mark A as visited. The last step is to pick a new node as a current node to explore this graph further, and therefore we always choose node with the current minimal distance in all our unvisited nodes. So when you look at our table, we have A with the distance of 0. But A is already visited, and we have B as an unvisited node with distance of 4. And we have C with distance of 2, and all the other node have distance infinity. So C has the current shortest distance of all unvisited nodes. This means that C becomes our current node. For our node C, we can now go back to our step 3 to calculate the distance of all unvisited neighbors of C. So unvisited neighbors of C is B, D, and E. And the distance calculation works as follows. Since C has the current distance of 2, we need to add this 2 to the weight of the edges to B, I, and D. Node B will have the distance 3 to plus 1 from A over C. This means we need to compare this 3 to our current value 4 in the table. And since 3 is less than 4, we set the current value for the shortest distance to 3 and we set the previous node to C. Node D will now have the current distance 6 from A over C. And now we need to check if 6 is less than the current shortest distance that we stored in our table, and the current shortest distance that we stored in our table is infinity. So 6 is certainly less than infinity. And so we update our shortest distance to D and set C as the previous node. Let's do the same thing as D. We will just repeat the process. Since 7 is less than infinity, we will just update our shortest distance to E and set C as the previous node. Now we are finished with C and let's mark C itself as visited. The next step is we choose new current node from all unvisited nodes again, and we choose node with a minimal distance. The node who has minimal distance is B, because it has distance of 3. We now calculate the distance to all unvisited neighbors of B, and in this case, we need to add 3 to the distance because currently the shortest distance from A to B. When we look at our table, so now we need to consider if we need to consider the distance of D, or we need to consider the distance of E. Let's start with D. The distance from A to B over D is 5. 3 plus 2 is 5, so 5 is less than our current distance 6 that we have sorted in our table. So now we need to update our shortest distance to D and we put B as the previous node. Next is E. The distance from A to B over E is 6. 3 plus 3 is 6, so 6 is less than our current distance 7 that we have sorted in our table. So now we need to update our shortest distance to E and we put B as the previous node. Now we are finished with B and let's mark B itself as visited. Now we have D and E left as unvisited nodes. and D has distance of 5 while E has the distance of 6. Again, we choose new current node from unvisited nodes. And we always choose node with a minimal distance. And the node who has minimal distance is D, because it has distance of 5. We now calculate the distance to the unvisited neighbor of D, and in this case, we need to add 5 to the distance. The distance from A to D over E is 6. 5 plus 1 is 6, so 6 is equal to our current distance 6 that we have sorted in our table. So we don't need to update it, and we just put D to the previous node of E. Now we are finished with D, and let's mark D itself as visited. This leaves us to the node E. Since E has no unvisited neighbors, so we're done here, and we can mark E as finish and put it to the visited nodes. And in our table, we have some important information about this graph. We have now the shortest distance from A to every other node in this graph, and we have the previous node, which helps us to reconstruct the shortest path. To find the shortest path now, we start at the node E, look at its previous node, which is D in the table, so we mark this node from D to E, and now we look at the D and see that it has the previous node B. So we mark this edge from D to B. And again we look at the B and see that it has the previous node C. So we mark this edge from B to C. And lastly, we look at the C and see that it has the previous node A, so we mark this edge from C to A. And now we have found our connection from A to E that has the length 6 and is the shortest path. Here is the pseudocode for Dijkstra'S algorithm.